In these two examples, we're going to find areas under curves, but we have a trig value and we have a fraction. So trig value, remember that we have to have a strategy, and this came from an original derivative, but anything that relates a trig value, it's a chain rule, which to undo a chain rule is a u substitution. And then same thing with this, we'll talk about that one in a second, is I'm going to take this piece inside the cosine and I'm going to let that be our u value. And I'm going to take the derivative, and that's going to get us a 2 dx. So I see a dx. That 2 is kind of inside the parentheses there, the cosine. And so if I pull that 1/2 over, that means that my dx right there, I'm going to replace with a 1/2 du. So I'm going to have a 1/2, and that's going to be a du. So what I'm also going to do is my cosine, instead of it being a 2x, I'm going to replace it. And so it's really a cosine of u du. Now here's the one difference is we were originally going from a 0 to pi over 8, but I'm converting everything into terms of u. So I'm going to convert my bounds into terms of u as well. All that I have to do for that is I take this value of pi over 8 and I plug it into this equation, because then that turns it into u. And so I'm going to take 2 times this x value, so 2 times pi over 8, which is pi over 4. And then I'm going to do 2 times the 0, which is still 0. So 0 to pi over 4 now. All right, so we have a 1/2, and we have a antiderivative of cosine. I don't really know, so let me kind of go through the path here. I know that the derivative of sine becomes cosine, perfect, and we're going backwards. So the antiderivative of cosine is going to be sine, so 1/2 sine x, not x, sine u, and we're going to go from 0 to pi over 4. All right, so 1/2 sine pi over 4 minus sine of 0. And sine of pi over 4 is 45 degrees. And so 45 degrees, sine of 45 degrees is root 2 over 2. Sine of 0 is 0. And if I distributed a 1/2 into that, I'm going to get a root 2 over 4. And then that's going to go away. And that would be my area under the curve. Now, remember, you could, if you don't want to change your bounds, then sub in the u, do your antiderivative, and at that step, pull your u back in. So it would really be 1/2 sine 2x, and then you'd still be going from 0 to pi over 8. But at the end of the day, when you take the pi over 8, you'd be multiplying it by 2. It's going to turn into this exact same thing anyway. So, all right, last one is something like this. Pretty frequently, whenever you have a denominator, that ends up being your u value, because then you create like a 1 over u. It has a very natural log kind of a feel to it. So one other thing that I'm looking for is if I let this piece be my u and I do the derivative of it, do I create the numerator? And if the answer is yes, then that's your u. But I go the other direction. If I take the derivative of 2 to the x, I don't get this, because where's that plus 4 come in? So that screams that the denominator is going to be my u. So I'm going to have a 2 to the x plus 4. All right, and now it's not a base e, so I'm going to get a little bit of a trickier derivative to it. So I do the derivative of 2 to the x. I get itself times the natural log of the base. And that's the piece we never worry about when it's an e, because the natural log of e just goes away. And then times the derivative of the exponent. And so the derivative of the exponent is a 1. Right? So nothing else tacked onto that, but then times dx. All right, so here's what I got. Let me rewrite this a little bit and see what I have and what I don't have and what I need to manipulate. So we're going to go from 1 to 3. I'm going to always pull the numerator off. 2x plus 4 times 2 to the x dx. Okay, well, I have a 2 to the x dx, but I don't have a natural log of 2, so let me pull that over to the other side. Equals 2 to the x dx. I definitely don't need that 1 on there. So this can be replaced with 1 over the natural log and du. Okay, and then here I have 1 over this value, which I'm going to replace with u. Now I'm going to leave everything in terms of u, just like we did here, which means we need to take this 1 and this 3, put them in, and let's get some new values, some new bounds. So we're going to take the 3, we're going to do 2 to the third is going to be 8, plus your 4 is going to create 12. And then here we plug in a 1, 2 to the first is 2, plus 4 is going to get you a 6. So those are our new bounds. So we're going to be going from 6 to 12 if we leave everything in terms of u. All right, so let's antiderivative this thing. So 1 over the natural log of 2 times, if I do the antiderivative of 1 over u, it is the natural log of the absolute value of u. And we're going to go from 6 to 12. So I'm going to pull this into at the very end. It's going to be the natural log of 2. And I'm going to be plugging in the natural log of 12 minus the natural log of 6. And we're going to do some simplifying. So here's where the algebra kicks in. Here's where your properties of logs kick in. You have a log that has the same base throughout the whole thing. So I'm going to be able to combine and do some things with this. So the natural log of 12 minus the natural log of 6, actually, okay, I'm not worried about the outside quite yet, that this is a property where you can condense your two logs together into one. And since it's a subtraction, you would take the first number minus the first number that's minus the second becomes the first number divided by when you condense it into one log. And then 12 divided by 6 is going to be the natural log. Sorry, rewrite this. So I have 1 over natural log of 2. And this natural log of 12 over 6 becomes natural log of 2. And then 1 over natural log of 2 is going to cancel with that, making your final answer to just be a 1. So that was finding the area under the curve and finding the area under the curve on the trig value.